Good morning from Singapore. It's a great pleasure to have Nicholas Rubin with us on the third talk of the series in quantum computing and quantum simulation. There are 2 or 3 more to go. The list is getting updated every week. We had the first talk by the Google group again on optimization 2 weeks ago, one more talk on quantum supremacy and analogous systems from my group. Today we have the recent work on chemistry by the Google group, and there are 2 more to go. Please check the list. So as I think now we're kind of more or less experts on this time, please keep your mics muted. Do send questions to me on the private chat. I'll try to pass them to the speaker whenever I can, and there will be some short discussion and some questions at the end as well. So, Nicholas, the floor is yours.
Thank you. Can you hear me?
Yep.
Give me a nod.
Yep.
Great.
Very good.
Well, thank you for inviting me to give this webinar. I would have loved to come visit, but this is almost as good.
We promise to bring you over as soon as it's doable again, and the world goes back to some sort of normality. Yeah,
that would be wonderful. But just as a quick intro, my name is Nicholas Rubin. Like it says on the slide, I work on the quantum algorithms team at Google. There are about 20 of us, and specifically, I actually work on quantum chemistry algorithms for quantum computers. I do a little bit of optimization stuff that Matt talked about last week, but I spend the majority of my time thinking about how we're actually going to simulate chemical systems with near-term devices and with fault-tolerant devices. So I'm going to tell you about some work that really spans a couple of years and culminated in this experiment that we ran on the Sycamore processor. It's one of the first experiments that we did after the supremacy experiment. And so things were kind of fresh and newly tuned up. And so one of the first things that we wanted to do was move away from just a random circuit sampling. And so that idea, doing some algorithmic primitive that we're going to have to simulate on NISQ devices and into the future in fault tolerance, is one of the driving kind of principles of this work. Okay. Let me see if I can change slides. Great. So I'm going to primarily cover 3 sections of this talk. I split it up into 3 areas, and I understand the audience it can be broad, and so hopefully there's something for everyone in the talk. I'll start off pretty broad and get into specifics about the experiment, but overall I'll just cover how we think about quantum computation for quantum chemistry, either in fault tolerance and NISQ, and I'll focus on NISQ. I'll describe our experiment, and then I'll talk a little bit about the error mitigation strategies and some of the things that we learned by actually running on the device, since I think that's probably the most important thing when people get a chance to actually run their experiments on the device. So I wanted to start off with actually a main goal of the Quantum AI Lab at Google, and that is to build a error-corrected fault-tolerant quantum computer. We know from our estimates of chemical simulation problems that would be interesting, and factoring we'll need on the order of 300 to thousands of logical qubits. And given some of the best estimates of the trajectory of hardware development and the threshold for the surface code, we kind of estimate that we'll need on the order of 100,000 to millions of physical qubits. So I've drawn this kind of qubit graph in terms of how many qubits you have access to at one particular time.
I like the logarithmic scale. I think this is important.
Yeah, I mean, it's kind of how we think now, I guess, or it should be how we think about things. But I think you have to start somewhere, and developing interesting and robust qubit technologies is somewhere to certainly start, and starting to integrate those in a scalable fashion is something that you can do at kind of small scales, order 10. And right around here, you can also start testing ideas from error correction. And that's really what I think as a field and that's moving towards building quantum computers really needs to start doing. There's some work certainly already demonstrating things like the repetition code and other small error correction systems. But once you're starting to get into the 10s, 20s, 50 qubits, you can really start testing some of the ideas and developing noise models that are tailored to the hardware and things like that, and really understand how maybe, for example, one might write better decoders, for example. But we know something kind of interesting happens around about 50 qubits. We reach the limit of what we can simulate classically in the most general case. Of course, we can simulate thousands of qubits if we're restricted to Clifford circuits. But it kind of signifies this kind of transition into a post-classical era. Now, one might ask, and I think that this is a very important question, what do you do between 50-ish qubits and 10 to the 5 qubits? And I think we're all probably familiar with the term NISQ, noisy intermediate scale quantum. And one of the things that I'm most interested in understanding is, can we derive some interesting applications for devices that are in this regime? Of course, we know that we're not exactly sure how long this regime will last, and so it would be very nice for the field as an error mitigation strategy, almost, to find some nice applications that one could use 1,000 qubits for, 1,000 noisy physical qubits. So one thing that I'm interested in, I mentioned I'm a quantum chemist by training. Quantum computers, one of the leading applications of them is simulating physical systems. And the types of physical systems that I'm most interested in are chemical and material systems. The motivation is almost obvious, making the kind of motivation for building a quantum computer tautological. If we understand these systems that are governed by quantum mechanics at higher fidelity, then we can go and develop better strategies for making man-made versions or making our existing chemical processes more efficient. For example, biological catalysis, nitrogen fixation is one very popular example. Hydrogenation is another. I think understanding protein dynamics in small molecules is obviously relevant for a lot of things that we're experiencing now. And of course, there are many interesting properties of quantum materials that generally get translated into technologies. I've kind of drawn a picture here of high temperature superconductor, but there's lots of other things, transition metal dichalcogenides and interesting states of graphene. So the point that we start at in terms of quantum simulation in the NISQ era, and that's the thing that I'll mainly be talking about, is one of the main algorithms that was actually developed by Jared McLean in 2013, who is now with our group at Google. And it's one of these algorithms that's in the hybrid class, or variational algorithms. So kind of from a high level view, the goal in quantum chemistry is to solve the electronic Schrodinger equation and get an energy given a position of a bunch of nuclei, namely the position of all of the atoms. Now, I've saved you from having to look at the interesting first quantized version. It's a partial differential equation. It has electron-electron interaction in it. That's the thing that makes it hard to solve in general. And so, like many classical techniques to solve the Schrodinger equation, these hybrid algorithms work by first positing a structure of the eigenstates and then parameterizing that structure. And so I've kind of written that here where I have this wave function and I parameterize it by some angles, for example. In QAOA that was discussed last week, they call them angles. In quantum chemistry, these are generally called amplitudes, but they are kind of the same thing. Namely, they're the input to a quantum circuit. And of course, the goal then is to minimize the energy with respect to these parameters. the energy here is the expectation value with my Hamiltonian describing the electrons of my system. And as I've written it here, it's not obvious why quantum computing would actually give you some type of improvement over classical. But if you imagine that this wave function, this thing that is prepared on our quantum computer, is doing something non-classical, namely, maybe we know a set of operations that are difficult to implement classically, and then we try to variationally optimize over this set, then we're in a regime where we can claim something like quantum advantage for chemistry. So overall, this kind of structure of algorithms where you use a quantum computer to prepare some function, that function is parameterized by the wave function, and then you evaluate an functional. In this case, it's the expectation value of the objective you care about. It could be the objective of a cost function you want for optimization. In this case, it's the Hamiltonian of my system represented in some basis. You then feed back that information, the expectation value or the energy, back into what the classical parameters defining your circuit, and you run this again in hopes that you can divine a set of parameters that minimize your energy. And so this is actually the guiding principle of kind of a lot of the algorithms that have been developed for NISQ. In nuclear physics, QAOA is an example of this, where the circuit structure is actually a little bit different. And then other machine learning algorithms, they're all kind of this flavor. The reason that these are kind of so interesting, at least from a NISQ perspective, is that they can mitigate errors. And so we know that in the intermediate regime of quantum computing, where we don't have error correction and we don't have fault tolerant operations, we know that our gates are faulty. Namely, they will do something close to what we expect them to be doing or would like them to be doing, but not quite. And understanding the errors and the ways that they behave is a very important part of the kind of march towards fault tolerance. But VQE algorithms, or these variational algorithms, work by kind of taking a more agnostic perspective and saying, well, there are going to be errors. I have this variational freedom. Maybe I can optimize around that variational freedom. Namely, if my gate over-rotates, for example, by 1 radian, then the variational optimizer will then want to under-rotate by that amount and thus achieving a lower energy. So it has been demonstrated that these can error mitigate, and that's actually what this experiment that I'm going to be talking about does. And what it does in kind of a unique way is that we demonstrate that you can perform error mitigation at the energy levels required for doing chemistry on a quantum computer, namely achieving chemical accuracy. Okay, let's see. So there's a lot on this slide, and I'll pause for a second to take it in.
Wow, this is the history of VQE.
Yeah, it's not quite everything, but it's certainly a large amount of it. I think I wouldn't be able to fit all of the VQE experiments onto one slide, but I hope to give you an idea about kind of how people like applying this thing. Chemistry is a wonderful target for quantum algorithm development and for quantum hardware development. And what I want you to take away from this is, one, the accuracies might look okay, but actually from a chemical perspective, they're quite bad. Namely, you wouldn't want to describe chemistry if you went to an industrial process and use a quantum computer to describe chemistry this way. And they all not yet. And they all involve fewer than 6 qubits. And so one thing that we wanted to do with this experiment is really kind of push ourselves into the regime where we have larger circuits and larger numbers of qubits, and really test the idea that you can variationally minimize, and VQE does have error robustness at scale and at the energy levels that we need for resolving bonding, for example, in chemistry. So that's kind of the perspective I have on kind of where we are in terms of NISQ, and what I wanted to do when you have access to a larger device that's very high fidelity. And so one question that we can ask is, general is, are we on a path to quantum simulation advantage? So like I said at the beginning of the talk, one strategy you can take is to look at what you're going to be doing in fault tolerance, namely take the best fault tolerant algorithms for Trotter evolution, for example, or LCU, and look at the algorithmic primitives that you're going to need to implement in that context. And then study that primitive on a NISQ device and understand how you can actually improve it as you're moving towards error correction. So one thing that I think it's important to note is that the NISQ era will be long. You know, we have many orders of magnitude in terms of qubits to make up, and so it will be quite a while, and it will overlap with the error correction era. So it's not going to be like one day there's a fault-tolerant error-corrected device of 1 million qubits going to work perfectly, and you know, we can all stop thinking about NISQ algorithms. There will be a transition, and it will be gradual. And I would advocate that ideas developed in NISQ actually are important for the error correction era because they can actually help reduce the required distance of your error correcting code. It lets us, so studying these things lets us understand strategies that will work best in mitigating noise, kind of mitigating noise at a holistic level. And it provides a benchmark for understanding our system. So of course, building a couple of qubits in isolation is an achievement and something that I think a lot of hardware groups aspire to, but building a full engineering system around it is a whole different ballgame. And really that's the type of, if we're going to find advantage with NISQ, then I think identifying or understanding how algorithms scale into the thousands of qubits range is required. For example, does our error model of component systems actually look like our holistic error model? That's actually, I would really like to know if, you know, I can predict the readout error for an isolated qubit, does that translate into the whole thing? And how far are we are we actually from achieving quantum advantage? So in this vein, and keeping all of these things in mind, the thing that we thought about doing is actually performing Hartree-Fock on a quantum computer. Now, Hartree-Fock theory is mean field theory for electrons. It is kind of one of the first chemical models or electronic models used to describe chemical bonding. It's as old as the field of computational chemistry itself. And what we do is we cast this procedure, which is not normally cast as a variational algorithm, as a variational algorithm that you can run on a quantum computer. And I'll get into why this specifically Hartree-Fock is important in a bit. But what Hartree-Fock does when you cast it as a variational algorithm is implement a basis rotation. So there's nothing fancy about this basis rotation. Imagine you have, you know, a dimensional, some Rn dimensional vector. A basis rotation would be a unitary operation or that takes that vector and rotates it to a different position. What we're doing here is kind of the same thing, except our vectors are now orthogonal orbitals for molecules. And so like I've drawn here, we can take our orthogonal cardinal vectors as these funny looking wave functions. These are one particle wave functions for this particular molecule. And a basis rotation forms a linear combination of these things, forming a new set of orbitals. So I'll claim, and hopefully it is at least to you, some of you obvious, that you can encode this basis rotation actually as free fermion dynamics. So if I set phi to be some computational basis state, the unitary that actually implements this basis rotation is governed by this particular equation here. The kappa values, actually the logarithm of the exponentiation of this kappa matrix corresponds to these C coefficients, and the dynamics generated by this particular sum results in a probability distribution that corresponds to the product of some of these orbitals. Now, it might not look like you can actually implement this without Trotter error, because we know that fermionic operators don't generally commute with each other, unlike qubit operators. But I'll discuss later how we actually do the compilation Trotter error free. But making the connection between a variational formulation of free fermion dynamics, if we variationally minimize the kappa matrix here, this number of these parameters that are going to go into our circuit, we get the lowest energy product state, which corresponds to the Hartree-Fock state. And so this is kind of a recasting of how one normally learns about the Hartree-Fock procedure. More formally, just mathematically, we're optimizing over the kappa matrix here, given the unitary that implements the free fermion dynamics. So why is this interesting? In some sense, it's not. It's trivially, or it can be efficiently simulated. One way to see that is that this particular, the generators here, these fermionic generators, form a Lie algebra that closes in n² operations, and so the adjoint matrix can efficiently represent the dynamics. It's performed quite often in classical computer or quantum chemistry codes to find ground states. But from a qubit perspective, free fermion dynamics is actually quite entangled. Basis rotations come up everywhere. Like I said, this is kind of drawn from some of the best algorithms we have for simulating chemistry in a fault-tolerant regime. We have an optimal compilation, and I added great benchmark here just because I like to think about this as like a baby version of what happened in the supremacy experiment. In the supremacy experiment, the random quantum circuits prepared random unitaries with respect to the Haar measure on 2 to the n by 2 to the n, on a 2 to the n by 2 to the n space. That was the size of the random matrices. Here we can implement free fermion dynamics, if we forget about the optimization with respect to some Hamiltonian, as a set of random unitaries on an n by n space, where n is the number of qubits. And so it's kind of like a scaled down version of the supremacy experiment, except we can efficiently simulate the output and we don't need a supercomputer. It's still very entangled and still is a challenging benchmark. And I said that stuff. Okay.
Just a quick question, Nicholas. So your fermionic operators say dagger, P's, and AQs. We can imagine that basically these act on the state and they create the orbitals. Can we imagine it like this, that each P and Q correspond to a specific orbital? So when you
yes,
right, that's a picture, right? So just for everybody understand.
Yeah,
but
we can.
When you go to the qubit space, usually you require another transformation, right? Like a Jordan-Wigner or something. So
yeah, I've left that off
out,
here because I think it's important to know that in general you need that. So let me first mention
entanglement and non-locality comes as well, right? Because these things are.
Yeah, normally we discuss kind of orbitals from a fermionic mode picture, namely one orbital is one mode, and we map one mode to one qubit. Mm-hmm. Now, if you directly kind of isomorphically, namely just label one qubit as one fermion, you won't satisfy the commutation relations of fermions, you'll violate the Pauli principle. And so you need to perform, in general, one of these transformations between qubits to fermions. But I usually formulate things in terms of fermions just because I think it's a little bit easier, and I'll argue later how that actually leads to a very efficient compilation of these things. But it's important to note that these are not qubit operators, they're fermionic ladder operators.
Okay, right. Good, thanks.
Okay, so why this obsession with basis rotations? I already kind of discussed that this is something that comes up in fault tolerance, but I want to make that a little bit more concrete. So let's say we start with a particular basis set that we're representing our wave function in, for example. Now, if you were to go and look at the electronic structure Hamiltonian, it has n to the 4 terms. Namely, it looks something like this if you were to relate a first quantized representation, go through the Galerkin procedure, and then write down the second quantized version, you get something with these products of fermionic ladder operators, and they're in general n to the 4 of these. So the molecular orbital basis leads to a fairly large number of terms in your Hamiltonian. We don't expect more than 4 because our original Hamiltonian only has 2-body interaction. And so this right here is the maximum that we can have. We know actually from recent work that, well, I think most physicists probably know that changing the basis can sometimes change the structure of your Hamiltonian, and it can change it in a way that actually makes it easier to implement a quantum circuit. For example, in this particular work, if you go to a specialized basis that kind of looks like a Fourier transform, you can take this 4-body term and actually reduce it into a square, a term that scales as the square of the number of orbitals or number of qubits you have in your system. And it's just a charge-charge interaction. Of course, you still have to implement this free fermion dynamics here efficiently, and that's what we're going to talk about here in this experiment. And that's actually just performed by this similarity transform. And then also some of the best strategies for measuring the energy of generally these Hamiltonians use this idea that you can actually rotate your basis, namely you take your problem and you break it up into many small pieces where each of the small pieces is represented in a different basis. That's that summation over the L's here. And in that basis, some of those terms are actually diagonal. And so this actually greatly simplifies the type of measurements that you need. And we actually show in this paper from last year that this actually can be achieved in an error-robust fashion. So we're definitely going to need these basis rotation circuits. I'd like to do them at the end of actually many electronic structure simulations. And so simulating them now as a jumping off point is, I think, a reasonable place to start.
We have a quick question from the audience this time by Vardan. Hamiltonian is generally basis invariant. Can you elaborate on it?
Well, yes. So I actually, I have this in one of the later slides. The electronic structure Hamiltonian is generally described in first quantization. Namely, it's defined as an operator that acts on position space of the position of the electrons. It has a Laplacian. It has a kinetic energy term. It has an electron-electron interaction term. Generally, if you want to solve this in kind of a linear algebra fashion, just like you would solve the E and M equations, you have to project this into a basis. I mean, this is a kind of a standard technique for solving partial differential equations on computers. The basis set that we pick actually is, there's a lot of chemistry involved in what is important, a good basis. But we want to choose a basis that kind of captures as much of the wave function oscillations as possible. And it turns out those wave function oscillations look like hydrogenic orbitals for most atoms. And so we can take things that look like hydrogenic orbitals and combine them into one basis, and then use that basis via the Galerkin procedure, which is effectively saying you project your Hamiltonian into this basis, and then solve the partial differential equation over that basis. So you're right, it is, the Hamiltonian is basis invariant, but you have to choose a basis to actually solve the system at some point.
Yeah, that makes sense, a basis that is relevant, yeah. Okay. Thanks.
So we know that we want to run these basis rotation circuits. We have a pretty good motivation for why we want to do them. Studying the performance on Sycamore is actually really important. And so how do we implement it on the device? For those of you who have read the supremacy paper, you probably saw the native 2-qubit gate interaction looks something like this. I'm calling here an FSIM gate, or we can call it a Sycamore gate, but really it's an interaction that's generated by an XX plus YY interaction, so a Jaynes-Cummings type interaction, and then it has a ZZ interaction, a C-phase interaction. I call it an FSIM gate here because it's a particle conserving operation, namely the 0,1,10 subspace of this 2-qubit unitary never leaves. There aren't any off-diagonal elements that would move me out of that subspace, and the 1,1 subspace isn't connected to anything else. If you wanted to actually recover, standard gate sets like an I-swap, you would set this theta to be something that corresponds to an I-swap and this phase to be 0. For the largest simulations we did in this experiment, it was 12 qubits, and so here I've just depicted, here I've depicted a Sycamore grid. I've highlighted 12 qubits in a line because actually our experiment only requires linear connectivity. And this goes back to the optimal compilation that we have for that free fermion dynamics. So what is that optimal compilation? I want to remind everyone the goal is to implement this unitary. We know that the generator terms here don't commute in general, but we can use this property that the generators form a small Lie algebra, and we can perform something called a Givens rotation. This Givens rotation actually swaps, it's a swap operation that looks like just the 0, 1, 1, 0 subspace of my fermionic simulation gate with no C phase here. And it allows us to actually decompose this unitary in a sequence of local 2-qubit gates. Classically, this is actually equivalent to a QR decomposition of the kappa matrix, also known as the Jacobi decomposition. And so what it does is it provides us an efficient way to go from the kappa parameters to a linear depth circuit. And so if you look at this circuit, it's actually depth 12. And the nice thing about that is that for all of the experiments that we study, we know the deepest circuit to optimally implement this particular unitary is the number of qubits. It's depth n, and there will be n squared operations. In general, this is what we have. So I want to unpack this particular figure a little bit more. In this experiment, or in this figure, I'm depicting the basis transformation circuit for a 12-qubit hydrogen chain, and hydrogen chains are something that we're going to look at a little bit later. These kind of blobs are actually the starting basis. So the basis that I start with, I actually get this basis from diagonalizing the Hamiltonian without any electron-electron interaction. Then it's just a one-body Hamiltonian that I can diagonalize. And we're working with real orbitals, and so the only phase component is plus or minus 1, and that's depicted by the color of these orbitals here. And so this is the starting basis set superposed with the 12 hydrogen protons. One thing to note is that we're simulating, of these 12, we're actually simulating 12 of the electrons, but we make the assumption that 6 of the electrons, namely half of the electrons, are spin up and the other half are spin down. This puts us into a singlet state for our Slater determinant, or our basis transformation. And thus I expect to be putting in 6 excitations into the circuit, and I expect to be getting 6 excitation out. Because all of these gates here actually commute with the number operator. Okay, so how do we actually compile this into gates? And one thing that I think is instructive, well, optimally, we could just say, well, I want to translate this theta to the theta value here and then zero out all the other phase components. Now, if I go to one of my hardware colleagues and ask for that, they'd probably kick me out of the room. It's very hard to do that in general. It's much easier to tune up a very specific gate. In this case, we chose the square root I swap. And the square root I swap is actually really important. It's actually equivalent to a 2-qubit Fourier transform. And so what we do is we Fourier transform, and we rotate the basis into the eigenbasis of one of these Givens rotation operations. We perform the evolution in that eigenbasis, and then we go back. If we just add pi's here, this just transforms this operator into square root I swap dagger. So things to note or to take away from this, our compilation of the basis rotation circuit involves 2 square root I swaps per gate per Givens rotation, and we have order n squared Givens rotations. It requires 3 RZ gates, and we actually implement these RZ gates physically. We don't do them virtually. And there's no Rx or Ry control. And so in kind of the superconducting qubit parlance, that would be there's no microwave control. And so we can do the RZ gates just by voltage offset. And this is actually an important point when you start to think about the error channels involved. We know that we can post-select on measurement because we expect that these gates are particle conserving. The square root I swap is just XX plus YY, and the Z gates commute with the number operator. And we can perform some other error mitigation. It's important to note also that these square root I swaps are around 12 nanoseconds. They're actually faster than our single qubit gates, which are around 24 nanoseconds. And so it kind of turns it on the head. If we were to implement microwave pulses with some other compilation, namely if we just used the Sycamore gate or CZ gates, then we would be introducing another error channel, and the circuit length would be much longer. Namely, the microwave pulses are longer than 24. They're around 40 nanoseconds. And so kind of when you think about writing down an algorithm, it's really easy to write down one of these grids and say how this is general. And But when you think about actually putting it onto the device, there's a lot more to consider. Okay, so the last step of the VQE procedure is evaluating my objective function. So I need to evaluate the energy. I was performing Hartree-Fock and I defined some Hamiltonian related to the chemical system I cared about. How do I evaluate the energy? Well, I formulated these. I claimed that the Hamiltonian for the electrons of a chemical system can be represented by the sum of these one-body terms and two-body terms. And if you actually look at a matrix of these expectation values, these form what are known as the one particle density matrix and the two reduced density matrix, the one RDM and the two RDM. And these are quantum marginals, so they describe everything that is required to get the energy, but they're fermionic, so they correspond to long-range qubit correlations. Regardless, all you need to do to evaluate the energy of any chemical system is to evaluate all n to the 4 of these expectation values. For the basis rotation circuits, we actually have a very special scenario. We can directly relate the terms in this this 4-ladder operator term to the 2-ladder operator term. Namely, everything in the tube RDM is exactly determined by the 1 RDM. And the way to rationalize this is that we start in a computational basis state and we ask what the expectation valuator of these operators are, and you can just apply Wick's theorem. And Wick's theorem tells you that all you need is the expectation value of these 1 RDM expectation values. So that's a very special thing. For this experiment, it reduces the number of measurements we need quadratically. We also developed some strategies for optimally measuring this later, which lets us further reduce the number of circuits that we actually need to measure. We actually maximally parallelize all the measurements of the 1 RDM. Something that's actually very near and dear to my heart is understanding the geometry of these quantum marginals and how we can actually use them to error mitigate NISQ algorithms. And in this case, the geometry of these 1 RDMs is actually exactly known for Slater or for basis rotations. We know that their trace should give us the number of electrons. They should be idempotent operators and they should be positive semi-definite. Namely, they should be probability distributions of the electrons. Now, if you were to kind of pictorially represent this might actually look like some kind of pointy polygon in eigenvalue space of the 1 RDM. But all I want to claim is that you can use the fact that you should be measuring an idempotent operator for any basis rotation state and design a purification strategy. Namely, I would like to find the nearest idempotent operator given the one that I've measured that satisfies all of these conditions. And the thing that does this purification is this actually fixed point iteration. It's classically called McWeeny purification. Pictorially, what it does is if we're off somewhere in operator space or Hilbert space, and this is kind of getting a little bit technical, so bear with me for one moment. We'll get to the data soon. If you start somewhere off in Hilbert space and you don't satisfy the idempotency criteria, if you keep iterating this procedure here, namely raising your density matrix, your 1 RDM to the 2nd power and subtracting that from the 3rd power, you'll get closer and closer to the manifold of idempotent operators. So in general, we actually know a lot of the structure that the 2 RDM should have. And so you can just start designing more general error mitigation strategies. What I've described here is only applicable for basis rotation states. But it is important to note that we are working on things that can be generalized and kind of work in a more in a larger setting. Okay, so really quickly, just as a recap of the device, Sycamore is a 54-qubit planar array of transmons with tunable coupling between each of the qubits in a square array. I mentioned the surface code earlier. You should think a square array. Here's a picture of the chip and a picture of our CEO next to a fridge for size. I pulled this out of the supremacy paper, but the takeaway from this table, I think, that I would like people to see is this number here, that when you perform a 2-qubit cycle, and what I'm defining here as a cycle as on every pair of qubits, we're going to perform a set of single qubit gates and then a 2-qubit gate. And we're going to do that everywhere across the chip simultaneously. On average, we're looking at about around 1% error for doing gate operations across the chip. And then our readout is mostly limited by T1, around 3%. You can actually back of the envelope this with a 1 microsecond readout and average 35 microsecond T1 time, your decay is about 3%. And so that's exactly what we see. Most of the data that's collected for this experiment, we use Circ, which is our open source framework for composing quantum circuits and writing quantum algorithms, and OpenFermion, which is our package for translating chemistry problems to quantum algorithms problems. So how well does Sycamore do? We have this nice primitive, we have a compilation, we know what we're going to measure, we have some error mitigation strategies. What's the performance? So just as a reminder, again, this is the circuit, and this is the circuit for a 6-qubit experiment. This is actually the circuit for a 6-hydrogen experiment. And what I'm going to do for this slide is I'm going to solve the Hartree-Fock equations classically, which gives us these kappa values, right? I'm going to implement the circuit that corresponds to that and then see how well I do in terms of energy of my system. And then I'll also talk about fidelity later. So for the 6-qubit system, which, as I said, corresponds to the 6 hydrogens, what we're going to do is a classic benchmark in chemistry is to dilate our linear hydrogen chain. Namely, we're going to pull apart all of the hydrogen bonds. And we're going to see how our method scales with respect to the exact answer, because this is an efficiently simulable system. So the yellow points are what I'll call the raw data points. Namely, we don't apply any error mitigation. The green points are what we get for post-selection. And then there are 2 other data points on there that you can't see in this set. There's a blue data point and a red data point. And that actually applies, the blue ones apply this purification technique that I was just talking about, this fixed point procedure to the 1 RDM. And the red point combines all of those error mitigation strategy and does VQE. And so it seems like, well, the raw data looks pretty good. It certainly is pretty far away, definitely not what we would consider chemical accuracy. But once you get to starting to apply standard error mitigation techniques, it becomes indistinguishable from the line. And I'll blow up this picture in a second. The point of this is actually to see how it scales. So I said the largest experiment that we did was 12 qubits, but we certainly did 2 others in between. We did an 8-qubit experiment. Again, we see similar strategies, and I've actually, in this time, plotted an inset where this is the energy error with respect to the exact solution, and this dashed line is chemical accuracy. So with VQE, we are actually getting below chemical accuracy for this particular rotation at 32 square root I swaps and 48 RZ gates. Now, this is already the largest, this is already beyond the largest chemical simulation done to date on a quantum computer, but we can keep going. And we don't quite achieve chemical accuracy for the last 2 systems, but we're definitely seeing a large reduction in the errors as we apply error mitigation. And that's kind of the purpose of this. You know, we're starting from the optimal values, and then we want to see how much we can go, namely how much variational relaxation actually helps us in terms of mitigating coherent errors. And despite our best efforts for calibrating these devices, the fact that VQE works shows us that we still have a little bit of ways to go, and we can actually we can variationally optimize around any coherent errors in our system. Okay, so I promised.
Nicholas, this is all Hartree-Fock for the classical exact case as well, right? There's no interactions here anywhere.
Yeah. No interactions.
Everywhere, yeah, okay.
I'm not going to introduce interactions. If I go back actually to this slide, to introduce a charge-charge interaction, namely a Coulomb interaction between local fermionic modes, all I'd have to do is actually implement this e to the I phi, not zero it out.
Yeah.
And that would actually take us beyond what is efficiently simulable right away.
Right, yeah.
So that's actually a very good point. That's part of the reason that this is a very interesting benchmark. It's functionally, from a circuit perspective, very close to what we want to be doing for optimal Trotter steps. Yeah. I've just selected it such that I'm only simulating match gates, and so.
But then you can build
fermionic.
Yeah.
Yeah, and so we can build on that. These fermionic simulation gates are in the match gate family. They're a particle conserving version. Okay, so I promised to zoom in of that. There's one of my colleagues once told me that you shouldn't believe anything unless you see it happen over 2 decades on a logarithmic scale if you're trying to do an experiment. And I actually like that maxim. It's kind of hard to draw a line and on a log scale without actually seeing it happen over 2 decades. And so I wanted to see that with our variational algorithm. And so I've selected 3 points from this curve here and applied, or I'm showing you the trace, the optimization trace of VQE. And we're pretty consistently optimizing over 2 decades. And so I would claim that VQE is mitigating errors without some fluke here at the precision required for doing chemistry. A kind of fun fact for this experiment, we get the gradients, you can get the gradients in general by something like a parameter shift rule. For these experiments, we actually only need the 1 RDM, that matrix of n² expectation values, to estimate the gradient. The deeper mathematical reason for this is that, again, the generators of the circuit form a Lie algebra that closes at n² terms, and therefore everything is efficient to do in general. But we design a new gradient-based algorithm here that actually uses second-order information. That's also a first for VQE. Surprisingly, despite the noise in the system, it was stable and obviously optimizes over a long period of time. These experiments are not particularly long. At least the 6-qubit experiment doesn't take very long. This is about 10 minutes worth of data to do. The rep rates of the machine is around 5 to 10 kilohertz. And so you can get quite a bit of data considering that we're measuring a reduced number of operators with respect to the full Hamiltonian. So that kind of allows us to.
How does that compare to the supremacy data collection time? Like on the, as you said, this is a few minutes to hours. In the other case was days or? Well,
so the supremacy experiment, we run it in a couple 100 seconds. The rep rate of the device, though they're running a much longer circuit, you're still dominated just by the readout time. And so the reset time of the device is about the same. It hasn't changed. And so the reason that these experiments take longer than 200 seconds is because we have to sample statistics for n² terms in my 1 RDM. Namely, all of those fermionic mode correlators I need to measure. And just doing that takes time. In fact, I have to prepare different circuits, and it takes more time to load the FPGAs and then do the measurements after that. It's not just one single circuit like in the supremacy experiment.
I see.
Another thing, and I think actually the hallmark of using these fermionic Gaussian states, these basis rotation states as a benchmark, is that you can actually extract fidelity. And I saw Jens Eisert is talking in a couple of weeks. He actually wrote a PRL on how you actually derive a fidelity witness based when you're restricting yourself to fermionic Gaussian states. And Hartree-Fock states, these basis rotations, are the particle conserving version of that. And so you can derive a fidelity witness just based on the thing that we measured for the energy, the 1 RDM. A fidelity witness is something that gives you a lower bound to the true fidelity. So you could give it the true state and it'll give you the true fidelity. And if you give you any other state, it will actually lower bound the fidelity that you would get, which is a very nice property. It means that we can use this as an efficient fidelity witness. Namely, we only need the 1 RDM, we've already measured it. We don't have to make an exponential number of measurements, namely perform full state tomography to reconstruct the state. And so on the right here, I've plotted the energy error with respect to the 6 hydrogens. So we've already seen that. We get well below chemical accuracy for some of the points. And I've also plotted the fidelity that we prepare each state with respect to the various error mitigation strategies that we apply. So for these, what I consider raw states, namely there's no error mitigation applied, we're at around 60% fidelity. And that just increases as we apply post-selection, purification, and the VQE, the variational relaxation. So we get about 2 orders of magnitude improvement going from just applying kind of standard error mitigation techniques. One thing that we think about in terms of these error mitigation techniques is what are the types of errors they're mitigating. We know that we should have particle conservation in our circuit, and we know T1 is the primary error for photon loss in our circuits. And so post-selection, namely we're fixing the particle number, we're projecting it into the desired particle number, is mitigating T1. You can actually show that T2 is actually fixed by purification. And the way to see that is a Z operator, which is kind of this stochastic form of the T2 operation, actually implements a fermionic rotation of a local gate of pi over 2, I guess. And so if you have stochastic Z errors in your circuit, you're actually forming a linear combination of Slater determinant states. And so purification actually takes care of this. And of course, variational relaxation, then you're mitigating coherent control errors. And so the biggest gains are purification and variational relaxation. So I've plotted these here. There's a lot of numbers on this table, but I think you can probably get the trend overall. These are the Fidelity witness numbers for all 4 systems that we looked at. The blue column is actually the supremacy error model. And so what this shows, given that it matches the raw values fairly well, is that we are mostly seeing the supremacy error, the error model that we posit in the supremacy experiment, despite the fact that we're actually not simulating a random circuit, which I think is actually quite interesting. Now, there is a bit of a disagreement here on the bottom. We expect that the fidelity witness here is trivially loose. Namely, this is a lower bound to the true fidelity. And so as the fidelity gets worse, this gap grows, right? But as you see, as we apply post-selection and then purification and variational relaxation, we get dramatic improvements in the fidelity. There's a pretty big improvement for post-selection, just because the fidelity witness is actually very sensitive to photon loss. The way the fidelity witness works is that you measure this 1 RDM and then you actually rotate it back to the original, as if you didn't, trying to undo the basis rotation circuit that you just did. And then you kind of sum up how different the occupation numbers are. And so if you don't actually account for occupation number loss, then you have actually a dramatic loss in the fidelity. And accounting for that, that's why there's actually a very big jump here. Okay, so this is the last example. I'll conclude with this, and this is kind of my personal goal, or it encompasses some of my personal goals with quantum computing and quantum chemistry, and something that actually hasn't been done in the field, using a quantum computer to resolve a chemical mechanism. Now, Hartree-Fock doesn't get many chemical mechanisms very accurately. In fact, these curves here, the sharpness of this peak should be pretty suspect. Usually nature isn't so non-regular. The molecule that we're looking at and the mechanism that we're looking at is something quite simple. This is a diazine molecule. It's 2 nitrogens and 2 hydrogens. And the mechanism I want to study is the rotation between the cis configuration, if you remember from general chemistry. Cis is where things are on the same side, and trans is where they're on different sides. And the chemical mechanism, or the reaction, what would describe by the reaction coordinate, is the transition between a trans conformation to a cis conformation. And so every point along here is a different nuclear configuration. Of course, I can simulate this classically very efficiently, and that's how I get all of the nuclear configurations. But I just want to see if my quantum computer can actually get these states properly. Getting this gap properly is actually the main goal. Hartree-Fock gets this gap wrong. In fact, this transition state should be below the other one if you actually include all of the electron correlations. So that's a very natural thing to do right after this experiment. Let's just add back in the correlation and see if we can recover the correct ordering. But we expect, of course, there's an in-plane rotation. That's this going through this TS1, this red curve, and that's taking the hydrogen from here and just pulling it in the plane up to the cis position. And the out-of-plane rotation is taking it and then rotating your diazine molecule out of the plane, a dihedral rotation. So let's see how the machine does. Well, pretty phenomenal. I wouldn't have put it that way if it didn't. in general, we see the agreement in the energy surfaces where they should agree. These are not exactly the same geometries, but they're very close, and therefore we expect the two configurations to give us a similar energy. We are actually getting the correct solutions up here. And overall, I think this is actually after applying all of the error mitigation techniques. So if I was just to plot the raw numbers for you, you probably wouldn't see this curve at all. It would be off the scale of the plot. And so what is really required to resolve a chemical mechanism like this is applying all these error mitigation strategies and applying VQE. We still saw a significant improvement after variational relaxation. Namely, we are accounting for miscalibrations and incoherent errors or coherent errors. So that was kind of the main goal of the experiment, and I think we achieved it. We resolved this chemical mechanism. That's the kind of the first time, and it's the largest simulation that's been done. So I'm going to end maybe with just some thoughts. I just said this. We performed the largest experiment for chemistry. It has double the number of qubits and over 10 times the number of gates as prior experiments, and also it's orders of magnitude more accurate, which I think is a very nice jumping off point for simulating now correlated systems and understanding how the system behaves at those levels when we actually can't efficiently simulate everything. In some sense, you have to walk before you run. So this ansatz, the thing that makes it efficiently simulable, it corresponds to free fermion evolution or non-interacting fermions. It's Hartree-Fock when you actually optimize that basis. Like I said, it allows us to understand how to calibrate the gates, and we actually develop a new type of calibration specifically for fermionic simulation gates that will be coming out later in another paper, which actually allows us to get to these accuracies. We have error mitigation strategies that target particular error channels that are known. We might as well take care of them if we know what they are. Of course, we weren't able to get chemical accuracy up to 12 qubits. And so I think pushing past this regime into something that is actually not tractable, we need to actually very seriously think about kind of other strategies that we can use to simulate chemistry on these NISQ devices, or we just need to wait for error correction or bring it closer. And so I think with that, I'll end. This was a pretty big team effort. Obviously, the entire team helped in developing the Sycamore processor, the control electronics around it, the web interface that allows us to run these simulations. Specifically, I'd like to call out Charles Neal, who I don't think you can actually see in this picture, who helped me as a theorist and tolerated my nagging when we were running the experiment, and Vadim, who helped with some of the calibration stuff. And thank you guys for your attention.
Thank you, virtual clap. That was very, very good. Very illuminating. There are a few questions. I have one to start with, and then we'll go to this. There's a couple from the audience as well. What about the partial tomography bit, and building up? The larger the number of qubits, the larger the system you're trying to do, I realize you have this one RDM, the specific approach that you get away at the moment at least, but isn't that a problem later on, or how one can deal with it?
So you're saying overall that you're right. In general, we can't use just the one RDM to evaluate the energy of a general system. We need the 2 RDM. It's only for this very specific structured wave function that we have that relationship.
Yes. And the higher order as well, yeah.
Well, you actually only need the 2 RDM for the energy. So if you care about just getting the energy, and almost all properties that anyone cares about, actually you can determine whether a system is superconducting just from the 2 RDM, for example.
Yes. And how much more difficult is that? Like, can one try to do that for a smaller molecule, like smaller chains, or?
So it's quadratically more expensive. So we expect to be performing, quadratically more measurements than we perform for this experiment.
Right.
But you can actually use, I didn't talk about this, the measurement scheduling, because it's pretty technical in this talk, but you can actually use the same technique of optimal measurement scheduling to maximally parallelize measurements of the entire 2 RDM. And it's kind of the same strategy that we use in this experiment, where we just optimally parallelize the measurements of the 1 RDM. We do that actually by kind of just relabeling the qubits, namely they correspond to different fermionic modes, and then changing the angles of our circuit. And you can actually do this if you're using like a fermionic swap network. The structure of the quantum circuit doesn't change. It's just the angles.
Mm-hmm.
The amount of time you evolve.
And what about be going like the next order beyond Hartree-Fock, putting some correlations in, some interactions? Any plans for that? And what kind of molecules would you think would be doable the next, I don't know, 2 to 3 years or so with this kind of NISQ devices?
I think in 2 to 3 years, we can start showing, maybe to steal Garnet Chan's phrase, quantum relevancy. Namely, for quantum chemistry, there are very sophisticated methods for describing especially ground states. There are still challenging systems that one can look at, but it would, I think, be an interesting goal for the field, and I think it should be a goal for the field to edge toward beating or showing parity with these techniques in terms of robustness or time to solution in a couple of years. And we certainly have plans to do that.
See the questions on the chat. It's a question by Swan. In general, if I have a few atoms having different principal quantum numbers, and I would like to study the properties of the molecule being formed from these atoms, how can I map the associated Hamiltonian into the quantum circuit? I'll repeat, if I have a few atoms having different principal quantum numbers, and I would like to study the properties of the molecule being formed from these atoms, how can I map the associated Hamiltonian to the quantum circuit?
So I'm going to take principal quantum numbers as, maybe I'll take an example of that, or I'll answer for an example of maybe doing a different spin configuration. So I mentioned earlier that we simulate only half of the electrons in our molecule because I make the assumption that on the closed shell, namely my magnetic quantum number, in this case a principal quantum, in this case a quantum number, is fixed to be 0. The only change is to the circuit, where I would have to be simulating something, namely I'd have to simulate the other electrons if I didn't want to do this as z equals 0 assumption. Classically, this is actually called restricted Hartree-Fock. As for like the charge and things like that, we treat the nuclei classically, and so they're just fixed classically, and we have an electron-electron repulsion term in the Hamiltonian. Oh, I think someone asked, what is the classical optimizer?
Well, I missed that. Yeah, maybe yep, please go ahead.
I just clicked on the chat button. So in this experiment, we developed a new optimizer. It's actually kind of based on a fairly old idea. In Hartree-Fock, or in general in quantum chemistry, there's something known as the Brillouin conditions. And these effectively are saying that given a generator of rotation, namely something that would produce a unitary dynamics, at your ground state, the first derivative with respect to the parameter of that thing is 0. So namely, the commutator of the generator with the Hamiltonian and the wave function is 0. So we use that principle to actually iteratively determine via like a Newton procedure by expanding the BCH expansion up to second order, what are the optimal parameters that locally satisfy that condition. And then I keep doing that over and over again. So It kind of looks like gradient descent, but the closer analogy is actually we're iteratively constructing the wave function, and you'd have to actually concatenate all of these circuits together. But we use the fact that we can actually compact all of these circuits into the same circuit, the original size circuit we had before. That's property of this one electron Lie algebra, or this one electron Lie algebra. It's a homomorphism of the algebra.
Cool. I don't see any other question in my chat. Maybe that one have been to you directly. That's why I missed it. Any other question? You can send it on the everyone if there is. I don't see anything. Okay. In that case, thank you, Nicholas, again. Another virtual clap from everybody. And thank you all for joining in again. Okay, there's one question from Koch, is very difficult to pronounce the name. Will including EE interaction improve the calculation? Will including electron-electron interaction improve the calculation?
It would be a more realistic model of the chemistry. There's always a trade-off between model complexity and computational complexity. And in this particular experiment, I went to the extreme of simplifying the model at the expense of a boring model. It has very simple computational complexity, but we get a lot of stuff out of that, like fidelity, being able to address fidelity, understanding how the gate errors happen, things like that.
Yeah, right. And provides
adding electron and electron.
Yeah.
Electron-electron interaction will make this more realistic.
Yeah. That's the next step. Yeah. But now you have a benchmark. You have a clear thing how it works on the quantum processor side. What's the errors? What needs to be set up to go to the next step. Any other questions? Don't see any other. So thank you, and see you next week with a theory talk on some recent work on optimization, quadratic optimization, and efficient encodings. And thank you all for joining again.